Hi, I'm Xuan Shen. I will tell you how random CSPs fool hierarchies. This is John. You work with Hyujin and Sujin. To solve constraint satisfaction problems, a number of hierarchy algorithms were proposed, and I will tell you 4 of them. Consider the problem of checking whether an input graph is too colorable. One way to solve this problem is to look for a solution in level 3 of the bundle width hierarchy. In a level D solution of the bundle width hierarchy, to every small subset of variables, we pick a non-empty collection of satisfying assignments. In this example here, consider this subset S as shown in this graph. There are 2 assignments satisfying all the edge coloring constraints on S, namely the assignments 010 and 101. That means we need to pick a non-empty subcollection of satisfying assignments from among here and assign it to S. We have to do this for every small subset of variables. We now have many collections of satisfying assignments across different subsets. We have to ensure they are consistent in some way. The consistency requirement says that if we take the collection of satisfying assignments on S and project this to a smaller subset T, we get exactly the collection for T. Another hierarchy is the linear programming hierarchy of Rayleigh-Adams. The definition is almost identical. The only difference is that instead of a collection of satisfying assignments, we now have a distribution over satisfying assignments. So in this example, we now have a distribution over satisfying assignments on S. We also have a similar consistency requirement, which now reads the following. The projection constraint becomes a marginal constraint. It says that when we take the distribution over satisfying assignments on S and considering the marginal to subset T, we get exactly the distribution for T. Another hierarchy is the STP hierarchy. This time, we assign orthogonal vectors to satisfying assignments on every small subset. The STP hierarchy, as defined on this slide, is equivalent to the Larcher hierarchy, whose Lagrangian dual is the sum of squares hierarchy. The STP hierarchy is often used in approximation algorithms, including approximation algorithms for graph coloring. Finally, let me mention the affine integer programming hierarchy. In this hierarchy, to every satisfying assignment on a small subset, we assign integer weights. We require the sum of integer weights to be 1 for every small subset. The AIP relaxation was introduced by Brakensick and Guruswamy as a generalization of Gaussian elimination. This AIP relaxation solves free XOR as well as some interesting promised CSP that are not linear equations. So, I've mentioned 4 hierarchies. For each hierarchy, the lack of a level D solution implies the CSP instance as unsatisfiable. A level D solution of the instance, if it exists, can be found in time roughly n to the d. So if we restrict ourselves to constant level hierarchy, this gives us a certificate, a polynomial time certificate, that a CSP instance is unsatisfiable. For a general CSP, even if an instance is unsatisfiable, level D solution may exist, in which case we say that the CSP fools the hierarchy. Previous works identified many CSPs that can fool these hierarchies. For bounded width, if your CSP is so-called null-constraining, then it fools the hierarchy. For LP and STP, the condition is pairwise uniform or tilewise uniform. For AIP, lower bound is known for approximate graph coloring. For all these hierarchies except AIP, the lower bounds are optimal in terms of level, and they also apply to random instances. So for AIP, can we get linear level lower bound? What about average case? Linear level lower bounds are interesting because they give evidence to the exponential time hypothesis. Inspired by the tilewise uniform property, we generalize it to other hierarchies, bounded width and AIP, and we call the property tilewise neutral. We show that if a CSP is tilewise neutral for a hierarchy, then random instances has a linear level lower bound. This is already known for LP and STP, but is new for AIP. This is the first linear level lower bound for AIP, as well as the first average case lower bound. For bounded width, we improve the dependency on delta for some CSPs. So, what CSPs are tilewise neutral? The precise definition is in our paper. Here is all you need to know. If the satisfying assignments contain a Hamming of radius tau, then the CSP is tilewise neutral for AIP. In particular, free set is pairwise neutral for AIP and has a linear level lower bound. Braiskens, Guruswamy, Moshner, and Sivny considered combining these relaxations to get stronger algorithms, and they introduced LP plus AIP. In this relaxation, a solution consists of both the LP part and the AIP part. We first strengthen every constraint using the support of the LP part, and then we look for an AIP solution to the strengthened constraints. For example, if the LP solution contains this distribution, and if some assignment is outside the support of the distribution, then the AIP solution is forbidden from using this assignment and must assign an integer weight 0 to it. LP plus AIP is a single algorithm that solves every tractable Boolean CSP. They ask if LP plus AIP hierarchy can solve every tractable non-Boolean CSPs. This is interesting because the CSP algorithms, in dependency by Bluetooth and STOC, are highly non-trivial combinations of bounded width and Gaussian elimination. If the answer to this question is yes, then LP plus AIP hierarchy would be a simpler algorithm for CSP. What is known about the lower bound? The only lower bound is by Seattle and Sivny, the super constant level lower bound for approximate graph coloring. So what about linear level lower bound? What about random instances? Since we are proving lower bound, why don't we consider the strongest hierarchy, STP plus AIP? We show that if a CSP is tilewise uniform and tilewise neutral for AIP, then random instances have a linear level lower bound for STP plus AIP. Here, the definition of STP plus AIP is exactly what you expect. In terms of the dependency on n and delta, our lower bound are optimal up to polylog because it matches the STP upper bound. Concurrently, Seattle and Sivny show STP plus LP lower bound for other PCSPs, and their results are incomparable. Our results are the most interesting if you consider random free set. The more constraints, the easier it is to refute a random instance. At constraint density above square root n, there are polynomial time refutation algorithms. At constant constraint density, Feiget conjecture there are no such algorithms. Previous work ruled out hierarchy refutations at constraint density slightly below root n, and we improve the results to STP plus ARP. Previous LP solutions work like this. Each constraint has a townwise uniform distribution of assignments, and then a distribution to a constraint subset can be defined. By sampling independently from each constraint, conditioned on agreeing at common variables. In this example, these two constraints share the common variable x3. So the distribution mu on this constraint subset will sample independently from the two constraints, conditioned on agreeing at x3. The distribution mu satisfies the following crucial property. If some constraint shares too few variables with other constraints or with S, then a point conditioning on S, the constraint C becomes invisible and can be replaced with an independent uniform distribution to variables unique to C. So any such a constraint can be ignored and it does not affect the marginal distribution on S. Using this property, an LP solution can be constructed recursively. Our goal is to mimic this proof strategy to construct solutions for bounded width and ARP. For bounded width, how do we define mu and nu so that they satisfy the above property? Turns out there's a simple, intuitive solution that works. For AIP, how do we define mu and nu? There is no easy intuitive answer. In fact, just finding the right definition is non-trivial. See our paper for the definition. Now the free set has both an LP lower bound and an AIP lower bound. It does not immediately give us any LP plus AIP lower bound. The reason is the following. The only pairwise uniform distribution supported on free set is the uniform distribution on VXOR. LP and STP solutions in previous works assign this distribution to every constraint, strengthening every free set constraint into free XOR. But when every constraint is free XOR, ARP will reverse the instance. We overcome this obstacle with new LP and STP solutions that has full support. We allow a small fraction of constraints to be not townwise uniform. In our proof, we keep track of these constraints using augmented closure. This decouples the LP and STP part from the ARP part in our construction. We also generalize the STP solution by Kothari, Mori, O'Donnell, and Wismar using a generalized Efronstein decomposition. Efronstein is an orthogonal decomposition for functions from a product space. There is a subspace of functions for every subset S, and these subspaces are orthogonal to each other. We construct a new decomposition for functions spanned by small hunters. We replace subsets with what we call ancestor closures. We generalize the quadratic form and orthogonal subspaces in Efronstein appropriately into our decomposition. Our decomposition is structurally similar to Efronstein. When the instance has no constraints, our decomposition reduces exactly to Efronstein. The quadratic form here is commonly called a pseudo-expectation. And our orthogonal decomposition immediately yield an STP solution because it implies the quadratic form or the pseudo-expectation is positive semi-definite. I will end this talk here with open questions about upper and lower bounds for AIP. Thank you for listening.